So section 5.3, Fundamental Theorem of Calculus. It's going to actually have two parts. I have basically three things that it does. So it is going to establish a connection between the two branches. So we've done derivatives and we've done integrals, and it's going to actually connect them for us. And then it's going to allow us to take the derivative of an integral function. I talked about that today. And then it's going to allow us to actually evaluate definite integrals by just a method without trying to find the area under the curve. Okay, so for this first problem, I have the graph. You have the graph in front of you. I'll just quickly sketch it over here, guys, so that I can refer to it. Sorry, it doesn't really have to be that precise because you have it in front of you. Okay, this is 1, this is 2, 3, 5, and then 9. Okay, so the first thing here is I have what is an area function. Okay, so an area function gives the net area of the region bounded by the graph f and the t-axis from a to x. So all we're doing now is we're looking at an integral as an actual function. So let this integral be a function. You start at some number, so a is a number, x is any number, okay? And it gives you obviously the area. So here is the graph of f of t. The area function would be a of x equals -1 to x. So if I start at -1, I go to any x value, okay? And I find the area between f of t and the x-axis. That's this area function. Capital F starts at 3. Evaluate the following area functions. So what would a of 3 be? So a of 3 would just be what? Go to a. It would be the integral from -1 to 3 of f of t dt. Now, why are these two different variables? Because if this is x, this has got to be like a dummy variable. Okay, because x is standing for any x value, whereas t is actually standing for the independent variable of the curve. Okay, so look over here. You should be able to look. What's the area between -1 and 3? Looking at your graph, we should get -27. Why is it negative? Because it's below the x-axis. Okay, capital F of 3. So if you look, capital F of 3 would be what? Start at 3 and go to 3. Well, if you go from 3 to 3, the area is going to be 0. So I have -27 and I have 0. Okay, go ahead. You could try B. What's a of 5? So a of 5 would be what? The area under the curve from -1 to 5. So from -1 to 5, what's the area under that? So it would be -27 plus 3, which is -24. And then do a capital F of 5. So F would be from 3 to 5. So if I go from 3 to 5, it's just this little area right here, which is 3. So F of 5 is 3. Okay, and then A of 9 and F of 9, go ahead, take a second and do. You should get -59 and -32. Now, just to try to understand this as a function. So A of 3, we got -27. A of 5, we got -24. And A of 9, we got -59. So see how this is actually another function. So the area to 3 is -27. I could actually graph this as a function. So the area under this curve is actually another function now. That's all we're doing. Okay. Second problem is going to try to lead us into the fundamental theorem. Okay, so the second one talks about this trapezoid over here. So I have a trapezoid from 2 to some x value, and the equation of this line that I'm bounded by is 2t plus 3. Okay, the area a of x inside here is the integral from 2 to x of 2t plus 3 dt. Again, why are there two different variables? X is standing for from 2 to any number inside here. Okay, from 2 to x, where x is any ending value, and t is the actual independent variable of that function. Okay, so the first thing is just find a of 2. So that would be what? Find the area under the curve from 2 to 2 of this line, which is just obviously 0. Anytime these are the same, we know it's 0. There's no area because I don't have any width. Okay, a of 5 would say find the area from 2 to 5 underneath 2t plus 3 dt. Okay, which is just what? It would be, if this were 5, it would just be the area of the trapezoid. I know we all remember area of trapezoid is 1/2 times the height times base 1 plus base 2. Okay, so this trapezoid over here, if I look at it, the height would actually be this distance. So from 2 to 5, the height would be 3. Okay, the first base right here would be this y value. So if I plug 2 into the function, 2 times 2 is 4, plus 3 is 7. That would be the first base. If I plug 5 in here, I would get the next height. So 2 times 5 is 10, plus 3 is 13. So that's the area of the trapezoid. Okay, and if you do that out, we get 30. So the area of a trapezoid from 2 to 5 is 30, just by using area of a trapezoid. Okay, now the last one saying find and graph the area function a of x for any x greater than or equal to 2. So now it's basically saying, what would the area of this trapezoid be in terms of x instead of in terms of a number? Okay, so it's still going to use the same formula, 1/2 times the height. What would the height be from 2 to x? So if it were from 2 to 3, I would do 3 minus 2. If it's 2 to 5, I would do 5 minus 2. So this distance from 2 to x here is just going to be x minus 2. That's really the height of the trapezoid. And then the two bases would still be this and this. So now this is still, if I just plug 2 in, so it's 7. And the other one would actually be 2x plus 3. Because whatever x is, I would take x and plug it into the formula to get this height. So this would be 2x plus 3. So there's the area of the trapezoid if x stands for any ending value. So if you simplify this, it's just going to be a quadratic, guys. This is 2x plus 10. If you FOIL and multiply by a half, you get x squared plus 3x minus 10, which we could graph. It's a parabola. Okay, now the last question is saying compare the derivative of a to f. Okay, so now here's a of x. What does a of x stand for? A of x stands for the area under this curve, from 2 to any number. If you find the derivative of it, what is it? What's the derivative of a? A prime is actually what? 2x plus 3, which is the actual curve 2t plus 3. So the derivative of the area under this curve is actually equal to what I started with. Okay, that's really the first fundamental theorem of the first part to the fundamental theorem of calculus. Okay, so it says in all this jargon, if I take the derivative of an integral from some number to x, it's actually just going to be this function that I'm taking the integral of. Okay, if you take the derivative of an integral, so, and here's, well, we'll talk about that later. It's actually just going to be equal to f of t. Now, why does it change to x? Because when you do it out, the value would actually turn into x. Think about your trapezoid. To get the height, you actually plugged in the x to get the height of the actual rectangles or trapezoid in the problem. Okay, so this is just showing us how do you find the derivative of an integral. Well, basically this is telling me the derivative of an integral really undo each other, and I just end up with whatever function's here, but it's of x, so you're going to plug that x in. Okay, and I can kind of show you that the integral, hopefully we see from before, from the problem before, the area function, okay, that we got was x squared plus 3x minus 10, and the original f of t was 2t plus 3. So the area under the curve, the integral of this was actually the antiderivative, if you look at it that way. So an integral is really an antiderivative. The area under this was this, which is this and the antiderivative of this. X squared plus 3x plus minus 10. We don't know that value could really be anything, but that's the idea. All right, let's do some problems. How do you actually do this? Find the derivative of a function. So we want to find the derivative of this integral. Okay, it's really that easy. The derivative of the integral is just going to be this function that I'm actually taking the integral of. The only trick is now it's going to be what I'm going to plug x into that function, because now it would be in terms of x. That's it. There's my answer. The derivative of an integral is that. Now why? If you actually took the integral of this, you would get an antiderivative. If you took the derivative of the antiderivative, it would undo each other and you would just get what you started with. Hopefully that makes sense. Okay? How does this get harder? Instead of ending at just x, what if it's not just x to the fourth or something else? I'm going to do the exact same thing. The derivative of an integral is just going to be the function, secant. Now instead of t, it's going to be whatever this is, x to the fourth. Now times, you have to worry about if this isn't just x, you have to multiply it by the derivative of whatever that is. So times 4x cubed. You are not taking the derivative of the function. You're taking the derivative of the upper limit, whatever is there. Okay? Next one, what if x is down here? I don't want to go from x to 1, I want to go from 1 to x. From before, we know that I can just switch that by making it negative. So this is the same thing as the opposite from 1 to x of t over t plus 1 dt. Now apply the rule. Derivative of an integral is just equal to the function, plug in x. So it would be negative x over x plus 1. Okay? And then the last one, the derivative of the integral is just equal to the function, which is the square root of t plus 2. Instead of t, I have x squared minus 2x plus 2. Okay, so I plug this in here, and then I times by the derivative of the upper limit, which would be 2x minus 2. That's how I do the derivative of an integral. Okay, moving on. Second part of the fundamental theorem. Here's the big idea. How do you find the area under the curve? Okay. Basically without actually using rectangles and doing it all out. So the area under f of x from a to b, well, I hopefully kind of explained that the integral is just the antiderivative. So you find the antiderivative of f of x, which is capital F. You plug in b, you plug in a, and you subtract them. That's it. Okay? And I have it written again. The integral of f prime would just be, this just shows it a different way, but where capital F is the antiderivative of f of x. Okay, so hopefully if I do these, you'll see how easy this is. Okay, so find the area under the parabola. So this problem is really saying from 0 to 1, find the integral of x squared dx. You're not finding the derivative of this anymore. Okay, I am finding the actual area. So first, I find the antiderivative of x squared. So go backwards. X squared is the derivative of what? Okay, so it would be x cubed over 3. Remember your rule, add 1, divide by what the power is. And now you're going to evaluate that from 0 to 1. The notation you can use is find the antiderivative and then use this bracket with your numbers. Then you can actually plug the numbers in. So now do this out. Plug 1 in. Minus, plug 0 in. And that's the actual area under the curve. So I would have what, 1/3 minus 0, which is 1/3. That actually gives me the area under. We'll talk about why. I'm just kind of showing you how to do it right now. Okay, next one. What's the integral of e to the x? The antiderivative of e to the x is e to the x from 1 to 3. So that just shows that I've found the antiderivative. And now I'm going to go from 1 to 3. Plug 3 in, which e to the third, minus plug 1 in, e to the first. You could leave it like that. Okay? Pretty simple. Next one, antiderivative of x squared would be x cubed over 3 plus Antiderivative of 2x would be 2x squared over 2, which is just x squared. And I'm going from 3 to 8. Plug 8 in, so it would be 8 cubed over 3 plus 8 squared. That's just plugging 8 in. So now we have to be really careful. Minus, plug 3 in. Use parentheses here. So it would be 3 cubed over 3 plus 3 squared. Because it's this whole quantity minus this whole quantity. So make sure you use parentheses when you plug the 3 in after, when it's more than one term. If you do this out, we get, I think, 216.7. Okay, I'm just saving time, the math there. We have a couple more, 2 more here. Okay, next one. How do I find the, a lot of us did this wrong on the last test. Can I use the quotient rule backwards? I hope you're all saying no. In order to do this, you have to simplify first. So the first thing I would have to do is divide each term by t. I cannot find the antiderivative as is. When it's one term in the denominator, you divide everything by it. So first, I would change this to what? T to the 1/2 divided by t would give me t to the negative 1/2 minus 1 over t. I divided each term by t. Now I can find the antiderivative. Okay, now I can add 1 to this. So I get 1/2. Divide by 1/2, which is multiplying by 2. And then what's the antiderivative of 1 over t? Hopefully we say natural log. Okay, and I'm going from what? Fractions 1/16 to 1/4. So I divide both terms by t, and then I find the antiderivative, and now I'm going to plug my values in. So this would be equal to 2 1/4 to the 1/2 minus natural log of 1/4. That's the first number, minus, plug 1/16 then. 2 1/16 to the 1/2 minus natural log of 1/16. Okay. Again, I'll give you the decimal. It's a negative 0.886. There it is. Last one. This looks weird. From 3 to 6, the integral of dx over x. We'll just rewrite this. Rewrite the dx afterwards so you're not confused. So write the dx over here. So this is the same thing as 1 over x dx. And now hopefully a light goes off and you say, oh, the antiderivative of 1 over x is ln of x from 3 to 6. So my answer is just ln of 6 minus ln of 3. Using our log properties, hopefully remember when we subtract, we divide. So this is really the same thing as natural log of 2. Multiple choice question, you could see it simplified like that if you're given the exact value. Okay. Big idea here. Differentiation and integration are inverses of each other. They undo each other. Okay. Really 2 parts to this section. The first is finding the derivative of an integral. The second is this. How do you actually find the area under a curve, or how do you find a definite integral? First, the word definite just means where I have numbers here. Indefinite is if I did not have numbers there, if I just wanted to find the integral of a function. Okay.